We're back in section 8.3, working on page 528, number 64, blink. When two lights close together blink alternately, we see one light moving back and forth if the time between blinks is short. What is the longest interval of time between blinks that preserves the illusion of motion? Ask subjects to turn a knob that slows the blinking until they see two lights rather than one light moving. A report gives results in the form mean plus or minus the standard error of the mean. Data for 12 subjects are summarized as 251 plus or minus 45 in milliseconds. Find the sample standard deviation S of x for these measurements. Show your work. Now to find that, we're going to work using the formulas that we have. So in your resource packet, sorry, trying to locate mine. We have that when we're dealing with sample means, the standard deviation is sigma over the square root of n. Because we don't know what sigma is here, we're dealing with S of x instead. So we have S of x over the square root of n. And we know that that's going to equal 45, because that's what they gave us here. Then we're going to plug in what we know. S of x over the square root of 12 is equal to 45. Then just doing your algebra, multiply both sides by the square root of 12, and you find that the standard deviation here should be 155.88. Going on to part B, a hasty reader believes that the interval given in the report is a 95% confidence interval for the population mean. Find the actual confidence level for the given interval. Now notice when they told us up here, they didn't tell us specifically what was used. So we're going to be able to find that, and we're going to use our calculator to do so. So we know that t is equal to 1 because we had our standard deviation of 45, and it should be our critical value times the standard deviation. So if the standard deviation is going to be 45, then our critical value had to have been 1. So we know t is 1. Remember, the t distribution looks a lot like the normal distribution. So we have our set mean, which means we're going out one above and below. So we can take t CDF, t distribution, we're doing a cumulative density function, and we're going to use our lower bound to be -1, and we're going to use our upper bound to be +1, and our degrees of freedom is always 1 less than our n, and that makes that 11 for this problem. So then you can go to your calculator. Now I forgot to bring my calculator home today, so I'm going to use an app that I have on my phone that looks just like it. And I'm going to do second distribution, just like we did with our normal, our binomial, all of that. And I'm going to go down here to where it says TCDF, which is number 6. I'm putting in that lower of -1, the upper of +1, and my degrees of freedom of 11. And I'm going to paste that in. And I find that I had to have had a confidence level of about 66%. So we're going to do more things to get better at our calculator and use it to help us with our confidence intervals. But this just shows us again how to use the formulas for confidence intervals.